Let's consider our partial differential equation under steady state. With the steady state, our acceleration term will go to 0. Okay, so in order to solve numerically, we can simply perform a finite difference right, where the partial terms, partial of u with respect to x, can be written in terms of finite difference terms, delta u over delta x. And this way, with the help of initial and other boundary conditions, we can solve for the displacement u as a function of x. However, the finite element analysis utilizes something called an integral form. Of our PDE. And unlike the finite difference term where you're taking a finite difference of the displacement u and x, finite element utilizes an approximation function. U tilde of x, which is u of x, our exact solution, plus some error term. Okay, so following this, let's consider the approximation to the displacement as u tilde of x. Okay, now plugging this into our differential equation here, we can write e times u tilde xx plus f. Now, since this is an approximation and not an exact function, this will be equal to some residual amount which is not equal to 0. Okay, ideally we would like to find an approximation function such that a residual goes to 0. Okay, to do this, let's introduce the fundamental lemma of variational calculus. This lemma states that if a continuous function g of x defined over the interval a to b satisfies the following integral formulation, where integration from a to b of function g of x times h of x dx is equal to 0 for all sufficiently smooth functions h of x, then we end up with our functions g of x is equal to 0. Okay, in light of this lemma, let's consider the following. For any arbitrary function w of x, integration over the domain omega of a residual function r of x times w of x dx is equal to 0, then our function r of x is equal to 0. So what this says that if this formulation, the integral formulation, is true, if this is true, then that implies that our residual function would be equal to 0. Now, assume that, for example, our approximation function for displacement is equal to some constant a0 plus a1 times x plus a2 times x square all the way up to an times x power n. Okay, here all the coefficients ai are constants. Okay, so in order to find the approximation to the displacement, we can say that we have n unknowns which are ai that will require n equations. Now revisit our integral equation. Mentions that for any arbitrary function wx, this holds true, then our r of x is equal to 0. So then I can come up with n functions wix, and I can write n such integral statements. For example, r of x times w1 of x dx is equal to 0. Second one would be r of x times w2 of x dx is equal to 0, all the way up to integration over the domain omega r of x times wn of x dx is equal to 0. So that way we end up with n equations. Note that these functions wi of x are called weight functions. And the integral equation is called the weighted integral equation. And such an approach to derive the weighted integral form is called the method of weighted residual. And also known as MWR. Okay.